Hello, and today I want to talk about related rates in calculus. So these types of problems have to deal with relating different rates of changes in contextual applications. So I want to jump right in with an example. So I want you to imagine a ladder, a 5 meter ladder with its top 4 meters above the ground, and it's falling in a way that the top of the ladder is dropping at a rate of 1 meter per second, okay? So right now our blue arrow is showing us the top of the ladder is falling at a rate of 1 meter per second. We're 4 meters high, is the moment that we're considering, but the ladder is 5 meters long. It's up against the wall, so we can imagine kind of it sliding down until it just hits the bottom and it's completely flat 5 meters out. And we're wanting to ask how fast is the bottom of the ladder moving away from the wall? So the first thing is this problem, we should have enough information, right? Um, we want to figure out how to find it, but we have enough information. We have the length of the ladder, we have the instant in question, and we have the rate of change of the height. From there, we can find some way to relate it, but the question is how. So our first thing is that we're going to label this height from the top to the bottom as y of t. And the distance from the bottom of the ladder to the wall, we're going to label x of t. It always helps to label things to get our thoughts clear. Now we can relate x of t and y of t by the Pythagorean theorem. So x of t squared plus y of t squared is 5 squared. Now the left side has to be happens to be a function of time. That happens to be constant, right? 5 squared. But how do we want to proceed? Well, since we're talking about rates and we know some rates and we have a function of time, we can differentiate it. So since it's constant, any any d of t, right? Very small d of t, some change in time is going to move this function. But since it's a constant, that rate of change is going to be 0. So we're going to write this on the left side as the derivative of it is equal to 0. But we can compute the derivative. So on one hand, even though the rate of change is 0, we can compute it. And using the chain rule, right? We're going to use the chain rule here. We have 2 times x of t times dx dt plus 2 times y of t times dy dt. And all that's equal to 0. And the key here is now we know what x of t is, right? Well, first we know y of t is, that's 4 meters, that's a given. X of t is directly related to y of t, right? We have a 3, 4, 5 right triangle. You could use Pythagorean theorem to verify that x of t is 3 meters. And dy dt, well, it's negative 1 meter per second because the rate is negative since the height is going down and it's given 1 meter per second. So now we have an equation with really only a single variable dx dt. So we can solve for dx dt and we end up getting dx dt is 4/3 meter per second. It's really interesting how from this problem we can show that the rate of change of the height is directly related to the horizontal length from the wall. And I think the best way to talk about related rates now that we kind of have an idea of what we're going to be doing, we're going to be formalizing it, putting some steps to it. So we're going to start with the following example. A spherical balloon is being filled with air so that the radius is increasing at a rate of 2 centimeters per second. How fast is the volume changing when the radius is 6 centimeters? Okay, this is a lot, right? But first, what is it asking? Well, it's asking how fast is the volume changing. So it's asking for dv over dt. The next thing is we should probably draw some sort of diagram, some image of what we're talking about. So here we have a spherical balloon and we have a radius of r. So our first step should always try to be to label everything. So V of t is the volume of the sphere in centimeters cubed after t seconds, right? We're going to specify the units and the input. And R of t is the radius of the sphere in just centimeters after t seconds, right? And we can directly relate the volume and the radius, right? We know that the volume of a sphere is 4/3 pi r cubed. So that's going to be our second step, relating these two functions of time. So the volume is equal to 4/3 pi r cubed, right? Is all we're doing. And now that we have that, we want to use implicit differentiation, right? Like we learned already previously. We're going to use that, although we're really just talking about two functions of time. So of course the derivative are equal. But we're going to implicitly differentiate both sides now to get the dv dt is 4/3 pi times, we're going to use the general power rule, times 3 times r of t squared times dr dt. And finally, we're going to start plugging some things in and hope that things cancel out. So we're going to specify, we're going to say at the instant, what t naught seconds. We don't really care what t naught is because it's not relevant, but we're just going to say at the instant t naught seconds, let r of t naught, which is our radius, be 6 centimeters. That's the instant in question, 6 centimeters. So dv dt is 4 pi times r of t squared is just 36 centimeters cubed. And our rate, dr dt, it says that it's changing at a rate of 2 centimeters per second. The radius is increasing at 2 centimeters per second. That's our rate of change of the radius, right? So now we just have this expression that we can multiply out to get 288 pi centimeters cubed per second. Now, this next problem is rather interesting. So, a person who's 6 feet tall walks at a rate of 5 feet per second toward a street light, and that street light is 16 feet high. How fast is the length of their shadow changing when they're 10 feet from the base of the light? Okay, there's a lot to digest, but first we'll try to make a diagram. So, we have a street light, we have a man or a woman, I don't know, walking toward the street light, and we have their shadow shown on the right, and a light hitting them. So now that we have this diagram out, we want to label first our rate. Well, we're given a rate that the distance from the man to the streetlight is decreasing at 5 feet per second. So our rate is negative 5 feet per second. Now we want to probably find some, label the distance from the person to the streetlight and the distance, or sorry, the length of the shadow. So we're gonna do. And also we're gonna notice here that the easiest way in the future, we're gonna do this in a step, but we won't have these two triangles that are similar. So we're gonna come back to that. But first, we're gonna label everything. So x of t is the distance from the person to the light after t seconds, and y of t is the length of their shadow. Now, step two, now we're gonna use similarity of triangles to get the following equation. And doing some algebra, we can determine y of t is 3/5 of x of t. Okay, and now what's our third step? Well, it's to differentiate implicitly to get dy dt is 3/5 dx dt. And we know dx dt is negative 5 feet per second. So plugging that in, we just get our rate of change of the length of the shadow is negative 3 feet per second. And that's our answer. Our final problem can be a bit tricky, especially if you don't have the diagram. So let's just work through it. A trough of water is 8 meters in length. All right, so we're imagining maybe something 8 meters long, and its ends, right, are in the shape of isosceles triangles with a width of 5 meters and a height of 2 meters. Okay, so we have trough water 8 meters long with isosceles triangles at its ends. And we're going to write out all this information. So our width is 5 meters, our height is 2 meters, and we are given if water is being pumped at a rate of 6 meters cubed per second, at what rate is the height of the water changing when the water is 1.2 meters deep? Well, our first step is going to be talking about, labeling everything. V of t is our volume. We're going to say d of t is the depth of the water, and w of t is the width of the water, right? And remember when we're talking about the width, we're talking about this horizontal distance, and depth is the vertical of the water. So hopefully this diagram makes it a bit clear, more clear what we're talking about. And from here we have a cross section. Notice how it's an isosceles triangle with a height of 2 meters, and the other one has a height of d of t. And also notice how the easiest thing to do here is actually look at the two right triangles, right? Which is 5/2 meters and width of t over 2. So it might all be a bit confusing, but our second step is just going to be saying by similarity of triangles, these ratios are equal, and the twos, you know, even though we wrote half, really it's going to end up canceling out because it doesn't matter in the end. But when we do the algebra, we get that um 5/2 is equal to the ratio of w to the d. And the key thing here is to notice, what do we want to express? Do we want to express W in terms of D or D in terms of W? Now it's saying when the water is 1.2 meters deep, so we want to eliminate the width. We don't care about the width. We need depth, okay? So we're going to do W of t is equal to 5/2 D of t. And now we're going to express the volume, right? And it's a prism, so we're just going to take the cross-sectional area, multiply it by the length. So the area is half d of t times w of t, and the length is 8 meters. So we're just going to get half 8 meters times d of t times 5/2 d of t, or in total 10 times the square of d of t times meters, right? Just the unit there. Final step is to differentiate implicitly. We get d, the derivative of v is 20 times d of t times d prime of t. Now, I'm not going to write d of t because it can definitely confuse me. I'm just going to write d prime of t. And v prime of t over 20 times d of t times meters is the derivative of d of t, so it's the rate of change. Okay, now that we have this step, now is the easy part. We're gonna say let t not be the instance when our depth is exactly 1.2 meters. So now the rate of change is gonna be, we know the volume, the rate of change of the volume. We know what d of t would be, right? D of t not, we said, is 1.2 meters, and we're just gonna have the meters there, and we can plug it into our calculator, whatever. We get 0.25 meters per second. So what we're saying is that the depth is changing at 0.25 meters per second, that it's rising. Every second it's rising by 0.2 meters. Okay. So all of this just to show how different um different types of rates can all be related in different types of contexts of problems. So the key thing to remember is to draw a diagram, label, use some sort of, way to relate the equations, right? Most of the time it's going to be geometry, similarity, or volume formula, area formula, whatever it may be. And finally, just differentiate implicitly and solve.